Yes, Jamila. You have doubt in week 2 assignment? Okay, what doubts you have? Oh, what? Okay, 1 minute. The graded assignment, question number 11, right? Week 2. Okay. The answers you are not getting it. Let me solve this. may take 2 minutes. I'm solving them. It's not coming properly. Okay, I will check that. I think some mistake happened. Some answers have been mismatched. I will check with the team and get back to you. When is the deadline for submitting assignment to? Yesterday I said that. Okay, right. Let me check with them. Let you know. Okay? Yeah, Srivastava, you have any doubt? Yeah, what is your doubt? The same one. Everybody is telling the same thing. I will check with the team. Some mismatch happened, I think. Some mistakes have been made. I will check with the team and let you know. What? Question number 1. Steady state value. What are you asking? What is your question on question number 1? Does not exist. The answer will be does not exist. There will be 10 as a sinusoidal signal that will be averages to 0 over 10. So the steady state value will be equal to the constant signal magnitude, which is, it is in 10 units, right? Question number 8. It is convolution of e power minus t sin t. I think the answer key doesn't match with that questions. The people who uploaded that answers, who have given the correct answers, I think they have made some mistake. We will try to correct that, okay? And let me know. Oh, you are asking how to solve that? Okay, we can discuss that. Yeah. Yeah, you will get marks for it. It's compulsory. Yeah, you should write comments in this section. Whatever that is related to that, or you can write the same thing again in that box elaboratively. It's a kind of practice we have been doing for the first time this time only. So it is under testing phase. We also don't know. We are just started to check with that. So let's see how it goes. Okay, for the question number 8, somebody asked, no? We'll solve that first and we will proceed with the next one. Meaning you should find this. Okay? So first we unless and otherwise it was mentioned you have to follow the time domain based convolution, you can just go with the Laplace domain as it is easy, because the convolution will be in Laplace domains will be the multiplication than doing all the convolution work in the time domain. Right? So first we will try to find the Laplace transform for the signals. There are two signals. We will call this as f of t and this is g of t, sin t. Okay? First try to find what is the Laplace transform of this. You remember what it is? Right? E power minus at. So the Laplace transform will be 1 by s plus 1. For sin t, what is the Laplace transform? Sin at what it will be? Right. So since here a equal to 1, we can write it as g of s is equal to 1 by s square plus 1 square actually. Okay? So since we are asked to do convolution in time domain, we are going to do multiplication in frequency domain or s domain. Right? So then this will become 1 into s plus 1 into s square plus 1. Then we have to do partial fraction s plus 1 plus ds plus c by s square plus 1. So if you take the partial fraction and find what is a, b and c, you will get the answer like a will be 1 by 2, I guess. A will be around 1 by 2, b will be again minus 1 by 2, c will also be 1 by 2. Then you will get something like this, 1 by 2 into s plus 1 minus s by, already this is there. So we are going to write this into two separate terms, like s by s square plus 1, 1 by 2 minus 1 by 2 plus 1 by 2 into 1 by square plus 1. We are writing this as a two separate terms. When we do partial fraction, we will get this. So we got this in Laplace domain, all the in summations like plus and minus, not in multiplication. Now since the options are in time domain, we are going to do the inverse Laplace transform of this. This is f of s into g of s. Right? We have to do inverse Laplace transform of f of s into g. If you do that, what this will be 1 by s plus 1, this will be 1 by 2 into e power minus t minus this will be cos t, right? Cos t, right? Plus 1 by 2 into sin t. So this will be your final answer. Is it clear? Any question number 11? See, this is question number 11, right? I have written straight away from that question. This will be y double dot double dash of t plus 5y dash of t plus 6y of t equal to 3x dash of t, sorry, x of t plus 2 into x. So when you take the Laplace transform for this, you will have this x of t plus 3 into y of t, right? So, but in the question it was mentioned that x of t t will be e power minus t into u of t. Let's take u of t equal to 1, then we will just consider x of t as e power minus t. So we have to put, once we find this, so we will take this. This is fine. This is question number 1. So once we find this equation, we are going to replace what this will be y of s is equal to 3 into s plus 2 by s square plus 5s plus 1 into x of s. Right? Replacing this x of s with, we have x of t means that is e power minus t into 1. Then when we find this will be s plus 1. So I am going to multiply s plus 1. Clear? Until this, is it clear? Right. So just we are going to do partial fraction again. So this will be 3 into s plus 2 divided by s plus 1 into s square plus 5s plus 1. Then we can factor this out. That will give us s plus 1 into, if we factor this 5, 3, will be 3 into, yeah. 6, 6, okay. Right, good, thank you. So you will get factors like this. So the common factor I am going to take it out, 3 by s plus 1 into s plus 3. Just do partial fraction for this, it will be easy. A by s plus 1 plus b by s plus 3. You will get the a value equal to 3. You will get the a value and b value. When you substitute that, I think I made another mistake. No, it's correct. Right, this is 3s plus 2 into x of s common. Right? You will get the a and b value, substitute that and take the Laplace inverse. You will get the value. You will get the answer. It must be some coefficient a into e power minus t plus or minus some coefficient into e power minus 3. I hope that option would be C. If this a will be 1 and b will also be 1. Right? I think that is the correct answer. Then what is the problem with 11? Jamila? Okay. What was the problem with question number 11? You would have chosen C option, right? Or do you have problem in finding this answer, or you made some mistakes on it? Okay, right. Is it clear now? Oh. Uh-huh. Mm-hmm. Okay. Yeah, that we also did here, right? Yeah, Laplace transform of x of t is x of s, right? Yeah, this will be 3 into, this will be 3s into x of s plus 2 into x of s. Taking x of s common, you will get 3s plus 2. Oh, here, okay. Yeah, understood. That mistake. Right. Okay. Oh, then you cannot make this one, right? This is not possible. Then this will be little bit difficult to find the partial fraction. It won't be straight. I think that is a mistake in the question. Yeah, we would have solved using this. If this question would have been 6, then this will be the correct answer, right? Then you have to do partial correction for all these things. If this is a question I'm telling, if there is no corrections in the question, then the answer will not be in the option. Then you have to do partial correction for these terms. 3s plus 2 by s plus 1 into s plus 2 s plus 3. So do partial correction for all these things. b by s plus 2 plus c by s plus 3, which will be equal to 3s plus 2, right? So you have to find ABC for all these things and substitute. Assume s is equal to then the options will be different. Three terms are coming, right? One e power minus t should come, e power minus 2t and e power minus 3t should come. Okay. Then we will give points to that. I will speak with the make corrections. Anything else? In there, any other questions you have doubts? Practice assignment question number 2. Find convolution. It is asked to find convolution of R of t into U of t, where R of t is a unitransit. That R of t is the common notation for unitransit. Okay, I will just show you here. Where U of t is the unit step signal with cos of t. So in the question that has been framed is little bit twisted. Sometimes I also got confused while reading this question. Just I'm going to explain it. There you have been asked to find the first you have to find what is R of t into U of t. Then you have to convolute this with cos of t. That is what the question is. First thing I want to make sure that this is the question. The next thing, what is R of U of t will be, if you want to do convolution, first step what we will do, we will just find the Laplace transform. Right? For finding the R of t, Laplace transform of R of t is t. R of t is t, Laplace transform of this will be 1 by s square, and U of t will be 1, Laplace transform of this will be 1 by s. Is it clear? Then what we are going to do, when we multiply this U of s into R of s, this will give us 1 by s square into 1 by s. Right? This is not convolution first of all. So what we are going to do is, we are first going to find only the R of t into U of t. What is R of t? R of t is t, u of t is 1. Then the multiplication of this will be t. That's it. So let me call this as f of t. So if I call this f of t is equal to t, then f of s will be 1 by s square, right? Is it clear now? Then the second function is cos t. For finding Laplace transform of cos t will be a by s square plus a square. That's it. So since it is cos t, I am going to call this as 1 by s square plus 1 square. Right? When we find the convolution for these two signals, f of t into g of t, where f of t is r of t into u. That is what the question is. Okay, this will be f of s into capital G of s. Then this will become 1 by s square into s square plus 1. Yeah. Right? That's it. You have to find the answer. That is the just don't get confused with the question. That's the one thing. Okay. Okay. We will start off with week 3 lectures. Let's pass half an hour here and we'll do a rush a little bit. So whenever we are coming for the live session, if you have seen some of the contents of the class week, that week particular lectures, it will be easy to discuss on the live session. So I know it will be difficult to watch all those lectures before coming to the live session in the first day itself, but try to go through that lecture, just make a look at it and then come back and you can ask so many questions and it will be easy for you to learn again when you watch this lecture. Okay. So this time, first week we got some introduction about what are all the systems, what is open loop, closed loop, and what is feedback and everything. The second week we got some introduction about the signals, what are all the types of signals exist, how we are using the signals to our systems, control systems, and what is control signal, input signal, output signal, and what is the error signal. All those things we have studied, and using that signal, how we are making that signal into a good form using some tools like Fourier transform, Laplace transforms, all those things we study. So these are all the basic building blocks. With this we are going to build one upon another. The next module is a bit difficult than the first 2 weeks. That is, this week we are going to see what is transfer function. Transfer function is a very introductory basics of the control system. So without transfer function, control systems does not exist. So it is a one form of representation of any control systems. So, okay. For example, I can represent mathematically how I am going to represent a fan mathematically. You will use dynamic equation. This is a more renowned form when it comes to control system. Mathematically, you can explain it using dynamic equation, but in a control system language, you will use transfer function as a representation. So we are going to see most of the things this week is going to cover only on the transfer function. What is actually transfer function? How we are going to use that, or what are all the ways it will be useful for our calculations, and what are the properties of those transfer functions. This we are going to see in details. So to motivate these things, why do we need any transfer function? We have given few starts or few responses of any systems. For example, if you see, I'm audible to all of you, right? Just give a thumbs up if you are with me. Right? Rest of the people? Are you with me? Okay. Manisha, Srivastava, Jamila, Vinayak. Are you people there? Give a thumbs up. If you are there listening to the class, give a thumbs up or just put a chat in the chat box. Right. Okay. Good. So we'll start off with this. Why do we need this transfer function? So if you see the left hand side image, these are all, we have a system. We have a system. We are giving one input to that system and we are getting one output. So this is the output responses plot of the system. Whenever we are giving signal, we are getting this responses for any particular system, for any some X system. Okay, we are not bothering about what system we are using. So this impulse, in the sense, we are giving impulse input. This step represents when we give step input to the system, the output response we call it as step response. This is step with disturbance. Some disturbance also we are adding here. This is impulse signal with some disturbance. Okay? These are all the different input signals we have given to any system, and we expect these are all the outputs of the system. So then the first thing, if you see impulse response, when I am giving an impulse response to a system, this kind of signal response I'm giving, the response was, it has started from some initial conditions like 5 and suddenly dropped it to 0. So this is working fine for me. At that moment it gave, according to the initial condition, it gave some value at 5, then it dropped to the 0, because after that there won't be any input signal, right? That is all. When we give input impulse disturbance, the same problem exists or the same condition exists, but this time you would expect some delay. This is because of the disturbances. Okay. Right. Now I am giving step response. Whenever I am giving step response, I have gotten the response started off with 0 but ended up having some value nearby this, but note that this is not 1. So in general, our steady state value will be equal to 1, but the signal is not settled at 1. Somewhere lesser than 1 it has settled. So when you do disturbances, it is again worse than that, because it settled way lesser than that. So in the right hand side response, if you see, the same impulse and step response I am giving. For impulse it takes some overshoot and at last it is settling. With disturbance also it is exhibiting same behavior. Not to complain anything, so it is working fine. For step response, if you see, there is a peak overshoot, but at last it is settling to 1, which is not here in this case. So this is working fine with step response. If you see step response with disturbance, then again it is a problem. There is a very big steady state error here. So you cannot, this system fails when the step is given using the disturbance. So keep these two responses in mind. We will see some other responses also. For example, in this system it is completely oscillatory signals. When you give some input, you got this constant oscillation. There is no convergence or there is no divergence. It is constantly oscillating around that particular point. And another set of signal, when you give it, you expect some convergence here. Okay? It is oscillating, but somehow it is getting convergence. That is good response. Here this is very good. It starts from 0 and settles as soon as possible. This is another response example where it tries to settle, but it takes too much time. It is considered very slow. And here in the right hand side, this is similar to that when it using impulse and step every time. This is very good. When you give step response, there is no steady state error, 0 steady state error. When you give impulse response, it settles to 0, impulse with disturbance settles to 0, and step with disturbance also settles to 0. This represents the disturbance has no effect in the system. So out of these 4 responses, which responses do you think exhibit better performances? Type it in the chat box. This is 1, 2, this is 3 and 4. What do you think exhibits the better performance? Four. Okay. Rest of the people? 4. Okay. Anybody have any different thought other than 4? Anyone have any answers for it? No? No, right? Yeah. 4 is the better one because it is giving no steady state error and it is giving good disturbance rejection. Right? An ideal system or ideal control system what we design is expected to give both of this. The steady state error should be low as possible and the disturbance should be rejected properly. Oh, then we have chosen this system as a good system. Then did you have any thought like how to make these systems, this worse system to make perform better? How can we make it? Or is it possible to make it? Or is it not possible, not at all possible to make it? If this is like the fate of the system, it will be like this forever. Is it so? We'll answer that questions in the later slide. So if we see this example, I was trying to point it this out, like this is a series circuit and this is the Ohm's law which is written having some mistake here. So this should be I into R, right? V equal to I into R. I of t into R of R. It should. So when you take this, it will be I equal to V by R. I of t is equal to V of t by R. Then this will become I of s is equal to V of s by R. Okay? Just try to correct this. Okay? Okay, then. Right, when you find the open loop transfer function, this will be open loop transfer function is feed forward thing. Whatever is there in the forward part, we will take that as a feed forward thing. That's why G of s is equal to R here, where we are giving some voltage to this. So we are considering 20 into 20 is the amplitude, and we are giving some sine value of frequency 10 of amplitude 20. That's what this represents. This physically how this voltage will look like. Okay. So when you want to try to represent this as a dynamic equation, this will be bit tedious, right? So I am going to represent this in the, if you want to write this as a dynamic equation and to find a solution of this equation, how will you find it? That's why we always convert this into the Laplace transform, where it is easy to find any relation between the input and output of the system, of any system. So here when we consider V of t is equal to this, finding the Laplace transform will give this, so V of s will be like this, and this for sine with all the notation, because they have given the explanation here how this will come, that we know already, right? So then I will become R into whatever V of s we are considering here. So when you try to find the solution for this, you will just do the inverse Laplace transform of this. That's it. Whatever value R value we are considering, that will be included with the, it is kind of, since it is a series circuit, we know the relationship, right? That was what the relationship it was mentioned here. That's for this kind of simple system, this is easy to represent, but for systems of higher orders like second order, third order, this will be difficult to represent like this. That's why we are going with the transfer function. So the transfer function can be officially defined as this is a Laplace transform of output by Laplace transform of input. When someone asks what is the transfer function, you can explain this with this technical explanation. It's a Laplace transform of output by Laplace transform of input. Okay? So we usually represent this like this. Q of s, y of s, where y is the output representation, u is the input representation always. Okay, how to find any transfer function? There should be some straight away method, or there should be some rule to find the transfer function, right? So first of all, you would be given all those things in a time domain region. U of t, y of t, r of t. Everything will be in the time domain. So we need to solve the ordinary differential equation first. Then we have to fill the model and we have to convert that to the first differential equation, or try to write or represent the system in differential equations. then build model relationship, how those parameters or how those variables are related to each other, then find the Laplace transform of those and try to write it in terms of Laplace of output by Laplace of input. That's it. These are all the 4 little steps you are going to follow whenever you want to find a transfer function of any signal. Right? The important point is transfer function will be useful for only the LTE system. For LTE system, it will be difficult to represent using the transfer function. That's why we'll go for state space representation. That will come in the next few lectures. Okay? Instead of transfer function, we will go with the state space equations. This will be useful when you go with multi-input, multi-output systems and higher order systems. Okay? Up to third order, fourth order, this transfer function will be helpful. Then every time whenever we are studying a new thing, kind of Fourier transform or Laplace transform, whatever it takes, we will start up with some known signal, right? So here also for transfer function, we are starting with some known signal. First of all, every time we will start with this impulse function. So whenever you want to represent an impulse function in time domain, it will be 1. In time domain, it will be 1 for value whenever the t is equal to 0, 0 elsewhere. So in Laplace domain, this will be represented as 1, right? 1 by s. Okay, fine. Laplace transform of step signal will be 1 by s. This will also be fine. Okay, fine. Then if we try to find the impulse response of this, then this will be 1. So when you are trying to represent u of s, y of s by u of s, this will be 1 into y of s. So whenever you are finding a transfer function, then it will be the Laplace of its output. That's it. Whenever you are giving input signal as simple signal. So if there is a system, you are giving impulse signal as input signal, then there will be some output signal in terms of Laplace I'm writing. Then if someone asks what is the transfer function of this system, this is the Laplace transform of output. That's it. Straight away answer. Or you can write it as Laplace of y of t. That's it. Right? Similarly, whenever you are using step function, this will be s into u of s. This will be equal to s into Laplace of u of y. When the output, for example, there is a system, so I am giving one step response and I am getting one sine value of frequency, let's take pi, and amplitude, let's take t. So how will we write this? 2 sine pi t. Then the Laplace transform of this will be pi by s square plus 24, right? 2 into pi by s square plus 25. So this is the Laplace transform of y of t. Then the transfer function would be simply s into 10 by s square plus 1. That's it. Clear? These are all for standard signals. Similarly, for ramp it will be s square into y of s. Parabola it will be s cube into y of s. That's it. So to cut short all those things, first you need to find the differential equations relating the parameters of the systems, that we called as model of the system. Then find the Laplace transform, then write it in terms of output by input. Laplace of output by Laplace of input. For that, the one step before this you need to find what is the output and what is the input. So these are all the steps that to find the transfer function. Okay. So we will give one example in each order of the system. For example, if we take a first order system, you all familiar with how the orders have been initiated, right? I think I already discussed this. Order will be equal to the number of energy storage element in the system. Right? Will resistor store energy? No. Right? Resistors won't store energy, but inductors, capacitors stores energy. So we can say in an electric circuit, for example, there are two inductors. We can say that this is a second order system, irrespective of what is the resistor or whatever it is. If there is one inductor, one capacitor, one resistor, then this will also be a second order system. So the order will be defined based on the number of energy storage element which is being there in the system. Okay. Fine. Now here there are one energy storage element, that's why this is a first order system. When we try to find write the KVL for this, then this will be V of t is equal to what voltage will be there here, V equal to IR. So this will be I into the resistance across it. This voltage across the inductor will be L into the voltage. Okay. How much the current varies with respect to time towards inductor value. So this is the overall KVL representation of the system. So if you try to find what is the input and what is the output, so we are giving, the power can be given in terms of voltage, 230 volt or single phase, 3-phase based on that. We will give power, so this should be the input, and we are getting the power in terms of output, like the energy in terms of output I current. So this will be the output. So first of all we wrote the dynamic equation. First step completed. Second step we identify what is the input and what is the output. Third step we have to find the Laplace transform. This will be V of s equal to I into R of s plus L into S into I of s. Right? Just try to this will also be I of s. Try to simplify R of s plus L s. Right? V of s. Then the next step would be writing the Laplace of output by Laplace of input. Then this will be Laplace of output will be I of s, Laplace of input will be U of s, will be equal to 1 by R plus S. Right? We got the transfer function. Now you understand how to apply this step. First step we have to find the dynamic equation. Second, identifying input and output. Third, write in terms of Laplace transform. Fourth, rewrite that Laplace transform equation in terms of output by input. Laplace of output by Laplace of input. Then you will get the transfer function as an answer. Right. So can you all solve the same with capacitor and put it in the chat box here? So instead of this just try to put a capacitor instead of inductor and solve it and put it in the chat box. If you have any doubt, ask. Just apply how you will write the voltage equation across any capacitor. 1 by C integral, you write like that. No? Instead of L dA by dt, put that and try to do all these steps and put it in the chart. What will be the transfer function, final transfer function? This one. Don't include capacitor, just remove this inductor and put capacitor. Power upon 1 minus everybody is getting this one. be like this, no? Another. Everybody is getting this? There will be integration, so integration will be 1 by s into, if it is x of t, x of s, this will be I of s. 1 by c already is there. So this will be 1 by cs r plus 1 by cs. Simplifying will get 1 rcs plus 1 by cs by rcs plus 1 or 1 plus rcs. Anybody have any doubt on this? Shall I go to the next example? Any doubt? Anything is not clear? So this is another example where we include all those things. So since there are two energy storing elements, this will be second order system, and writing the same that this two we know and this we know from the last example. So finding the Laplace transform will be r into I of s, L dA by dt will be s into L into I of s, this will be 1 by s into I of s. Writing all those things in a input by output form, you will get the transfer function. The another beauty of the second order system is this second order system has most of the control system engineers attention, because this can be written in a special form like this, where you can study the behavior of the system, right? Where omega n is the natural frequency and zeta is the damping ratio. So based on this, based on tuning this zeta and omega n, you can make the system to behave however you want. For example, if I want the system to behave like this, I can, by tuning these two things, I can make the system to go like this, I can make the system to go like whatever, or I can make the system to go like this. So by tuning these things, you will try to get the desired response. So this is a special representation of a control system when it comes to the second order energy system. Okay. This is another example, that is DC motor, that you can see from the lecture. There is nothing new I am going to tell here, just a combination of all those things we have seen so far. And try to solve this by hand, because some standard systems that have been there, for example this DC motor, servo system, mechanical systems like that involves both M, J and rotational systems that involves J, theta, B and simple pendulum, inverted pendulum. These are some of the very famous examples that we can use this to explain the basics of the control system. So whenever you see some or you learn some concepts in control systems, there will be an example from this combination or few other than this, but these are all some basic examples. So you should know how to write the dynamic equation or how to write the mechanical equations of this in a mathematical representation. So just sit and see the relation and learn how this works and what are all the principles behind this DC motor, Faraday's law, how if these are all, you can think that these are all very basic things, I can learn it in a minute, but give some thought to this. When you try to connect things with the basic laws, it will be evident itself. How this will be proportional, why the torque is proportional to current, why the back EMS is proportional to theta dot, that is angular velocity. How these things are being proportional, why people are proportional. Just sit and go through this, you will get some idea. But we will help how to write all those things. If you get some um, doubt in this, how to write and why we are relating these two, we will help you with it. But the basic thing, you should be able to at least write the dynamic equation. Then you can apply the control system concepts, Laplace transform, whatever tools you learn to make it in a better way to see. That's it. That's what we are learning in this week or in this module, like all those modules. Okay? Just try to derive this equation. Just derive this transfer function by yourself. It will boost your confidence. Then this is transfer function that is represented in both cascade and parallel. Cascade means one in series, one block with another block. Parallel means one block below one block, kind of this. The input will be same for all those things and there will be different things. When you want to connect two blocks series in series like this, resistor and inductor and a resistor connecting these two. So there will be a transfer function for this, or there will be a Laplace transform for this. How we are going to express this? This is just a multiplication of these two. That's a simple thing, nothing very fancy. Even if you interchange it, it won't change. Both are associated, both will be same. G1 into G2 and G2 into G1 will be same. And when it comes to same thing we had explained here. And when you come to parallel, this two systems will be added using a summer, where this will be represented as G1 plus G2 or G1 minus G2 based on this notation, whatever you are giving. That's it. There is no much difference in that. Then representing the open loop transfer function, how to derive this transfer function. So if you see a transfer function, this we call it as plan and this we call it as feedback. This feedback will be usually comes with a sensor's feedback. And closely if you see, this will be plus and this will be minus. So when we represent a system until this point, we were representing this as G of s, U of s, Y of s, right? So when you try to find the open loop transfer function, open loop in the sense only the feed forward open loop in the sense only the feed forward part, this part, whatever is there in the feed forward. It will be only G of s. But when you close the loop, when you close the feedback loop, what is the difference it is making to the open loop transfer function? So when you see, there is a signal called E of s here. This is called as error signal because we are giving one input, getting an output and considering the output back and giving it back to the system. So the difference between these two will be called as error signal E of s. Okay. So if I want to write the transfer function, I can write like, first of all, these are all the signals associated with the system. U of s, Y of s, E of s, H of s, G of s. With all these things we will try to find. First of all, how can we write the E of s? E of s is here. What are all the things coming to E of s? U is coming and B is coming. So U will be mentioned as plus and B is mentioned in minus. Then I can say U of s minus E of s, right? Clear? Right there. Now, I am to elaborate this step by step. What is BFS? BFS is the multiplication of YFS into HFS. So I can write this as YFS, UFS minus YFS into HFS. What is this? This is EFS. Right? So we got this equation. Done. Now, what is the output signal? What is the relation between the output and the input? Then output signal will be, this is the feed forward part. Only Y, for Y, what are all the things are connected? G is connected and E is connected. G of S into E of S. Where all the U, H are connected indirectly with this E of S. So if I elaborate this, then this will become G of S into U of S minus Y into H. Right? So this will be a entire transfer function. I will write it. Y is equal to G into of S. I am not writing now for simplicity. Okay. If you want to put output in the same location, how can I take this? GU minus GY into H. And if I want to bring here, this will be Y into GH into. Okay. So if I take Y as common, this will be GH plus 1 and this will be G. If I want to write it in terms of Laplace transform of output by Laplace by input, this will be G by GH plus 1. So the common representation will be G by 1 plus GH. Clear? So when the system is in open loop, only G of S, U of S equal to Y of S. Then the transfer function was only the G of S. But when the system is in the closed loop, the closed loop transfer function will be a bit complicated than the open loop, that this will be G of S by G of S into H of S. Clear? So this we call it as open loop transfer function. This expression we call it as closed loop transfer function. Here there is one catch where you have to be very careful with this notation. This notation is you have to be very careful. If I replace try to do the same logic, like I am rewriting the transfer function. This will be plus, this will also be plus. Okay, I am not putting minus here. This will be E of S, U of S, G of S, Y of S, will be H of S. Can you do the same thing? Yes, right. So this E of S here will become how it will be U of S plus B of S, right? Then this will be U of S plus H into Y. This will become UG into U plus GHY. Then this will be, if you take this Y here, then this will be 1 minus GH into G. So this will become Y by U become 1 G by 1 minus G. So this is the closed loop transfer function when the feedback sign is plus. This is the closed loop transfer function when the feedback sign is minus. So we call this as negative feedback. Closed loop transfer function with negative feedback. This becomes closed loop transfer function with positive feedback. So when there is a positive sign here, there will be negative here. When there will be negative here, there will be positive. This is the difference between these. To keep this in mind. But the elaborative thing you understood, right? You should not just heard it. Everybody is with me? Is it clear? Like, are you okay with this explanation? Okay. I hope everyone understood this. This is a very basic thing you should be strong in. Right? First, whenever you want to find a transfer function, that is particularly in closed loop transfer function, you should consider whether the feedback is positive or whether the feedback is negative. Then only you should write the transfer function. You will be able to write it properly. If it is an open loop transfer function, then it is very easy only to keep the same. Okay, done. So these are some examples you can go through later. Okay. Coming to the next thing. Quickly I will go through what are all the properties of the transfer function we have learned so far. First of all, the first criteria is that transfer function is independent of the magnitude and the nature of the input. So you can change the input like from sine to step to impulse. It won't affect the order of the system. That's what I was trying to say. This nature of the input doesn't affect the transfer function in the sense changing the input from one to another, it won't affect the order of the transfer function. And it is independent of the magnitude. Whatever magnitude you change, it won't affect the transfer function. Then using transfer function, response can be studied for various inputs. So just if you find the transfer function for any system, it will be easy if you change the input. First, if I give the impulse response, impulse input, I can change the step and just straight away find the answer. Instead of doing all the calculation every time whenever I'm doing, like in time domain, this will not be time consuming. And but one catch is the transfer function does not provide any information about the physical structure of the system because it is a mere representation of the system. It's not like a very mathematical rigorous explanation. For example, if you see the system, there is a mechanical system and there is an electrical system, RLC circuit and mass spring damper circuit. So here, based on this, it will only consider the number of energy elements in the system. And based on that, the order will change. Order of the transfer function will change. You will only get this knowledge about the system, not about what are all the energy elements. It could be spring or it could be damper or it could be inductor or capacitor. Both can be represented using the same transfer function. Only if you change the magnitude or the amplitude of that particular physical elements. So this is one catch of the transfer function. So there are few examples like in cruise control. In cruise control means it will automatically try to control the speed by itself. So it should not try to go over or below over. So you all know this cruise control, right? So how to write the transfer function? This is a kind of, you see some system in real time but you don't know how you can mathematically write it. So if you want to solve any problem in that system, you should be able to mathematically represent it. For that, this transfer function will be helpful. So this is the mathematical representation of a cruise control concept. And similar to that, there are few examples on the auto suspension system, mobile system, satellite attitude control, and as we saw some example in RLC, RA circuit, RC circuit. So these are all some other examples. You can see some how, or you can try to derive the transfer function using this block diagram. And with GS, few examples have been given. Sir has explained all these things. If you first go through the video, if you have any doubt, you can ask me in that Wednesday session. If you take all the examples, it will consume the rest. I will just go through, let you know the important points you should consider while studying. These are the lectures of this library on the example input. Okay, the third and most important lecture of this week is stability. So far we have been doing all these things just to find whether the system is stable or not. Why do we need stability? Anybody have any idea? It could be anything. No need to make any sense. Just whatever comes to your mind, just type it. Why do we need to find stability of any system? Why do we need stability? Why are we spending this much time in finding stability of any system? Okay. don't know is also a valid answer. Anybody got any idea? System will be? Oh, good. Oh, right. We will get to know whether the system will work properly or not. That is a valid thing. Then another important thing we are missing is try to relate with the this what is this course title. What is the course title? Control. Yeah. When you find the stability, then only you will know whether you will be able to control the system or not. You will be able to get the desired response out of the system. Right? If the system itself is not stable, how will you expect the desired response from the system? If you give 5, it will give 5,000 in a second. And you will not be able to control at all. It will be like this forever. You will not be able to make the system to work according to your wish. Right? So for that is an important point of finding the stability or understanding the stability of any system. This is for linear system, this is okay. For non-linear system, this might differ. That is of different levels of hardness. So we don't bother about it now. So first of all, the stability in linear time invariant system. That too in linear system we are focused on only the time invariant system. So a system is stable if it eventually comes back to the equilibrium. For example, if there is a bowl and I have some beans, let's say. So if you put this bean into a bowl, where this beans will go? It will try to go to the bottom of the bowl, right? So this we call it as equilibrium point. When you are any system, when you are giving a force or you are making some change, for example, based on the Newton's first law, unless you make some force or give some force or make any change, the system will be there until it is being touched, right? So when you give a force to a system, the system will exhibit some changes. And at last, where it is going to settle, that point is its equilibrium. So based on this only. So if you put some beans or any pebbles over this bowl, since the bowl is curvy, the minimum point, wherever the lowest possible minimum point, these pebbles will try to go and settle. So this is their minimum equilibrium point. This we will try to study whether this equilibrium point is stable or unstable. This will infer whether the system itself is stable or unstable. System whole gist about the thing, we will see one by one. So, for easy explanation, what they are telling is, if the system is stable, if you can find some equilibrium point, if you can get some lowest minimum possible or maximum possible point, then the system will be stable. Unless, if this is not curved, if this is like this, and the pebbles keeps moving in motion and it is not going to settle at all. I couldn't give some practical example for this, but if the pebble keeps moving, it is not settling at any, it is not getting settled at any point, then the system we call it as unstable. So it is, best example is the exponential system, which is not going to settle into this kind of curves, this kind of system exhibiting this kind of curves. So these are all unstable. Some stable, you can see this is stable, this could be stable, this could also be stable. And at last it should settle to some point, within finite time, not infinite. Okay. Am I audible now? Okay. So, then another important concept in the control system is bounded input, bounded output. That is BIBO. Whether the system is BIBO stable or BIBO stability. we call this. For example, this is very simple. Based on the name itself, you can say whenever we are giving bounded input, bounded in the sense within some region, within some interval, not it is a exponential, it is some bounded. Okay? Whenever we are giving some bounded input to any system, the system also, if it gives a bounded output, then we call this system as a reduced steady system. When I give bounded input, it is also giving bounded output. That's it. That is the reduced steady system. Okay. So mathematically, we are representing it like this. So the input is bounded using within some value. This m is some integer, let's say, or some other order based on your system order. It could be r power based on your system order. So this should be less than infinity, meaning this should be finite. Right? Whenever I am giving finite, I am expecting my output should also be finite. That's it. Or any other n. Right? If this system exhibits this example or this behavior, then it is reducible. So these are some of the examples of reducible where this settles here, right? This seems to be oscillating, but the amplitude is bounded here. So this is also a reduced system. Where these are all some non-reduced system, it keeps increasing, right? So this is not converging, this is diverging. As time increases, this magnitude will also get increased. Right? That's it. That's what it's like here also. So this can be explained using this expression. When you convolute two signal, input signal and your transfer function, whatever you are giving signal to, if you represent it in terms of convolution, I am telling that this is in convolution we will time shift this, right? But originally your input will be u of t, where the u of t is bounded. Lesser than m, some finite value. Right? So you can write this expression instead of u of t, I am just replacing it with the bound. This equality becomes inequality as we are bounding the signal within this finite region. Then this will become y of t lesser than or equal to m into only 1 g into tau dt. So if I can prove that this is lesser than infinity or some integer m, if this is finite, then the system is reducible. Whatever I said in the sentence, this is a mathematical representation of it. Then comes to another important concept, that is the pole zero representation of the heat system. So till now we have been representing our transfer function. So you should be bit conscious in this. So this is going to be the basic for the next few lectures. Okay? So till now we have been representing the transfer function as the Laplace of output by Laplace of input. Right? So we call this as 0 and we call this as pole. Right? The numerator of the transfer function is called as 0 of the system. Denominator of the transfer function is called as pole of the system. Usually, poles will be represented using this multiplication symbol. Zeros will be represented using this 0 symbol. Right? Poles will be like this, zeros will be like this. If I want to represent that pole of the system is in -2, I will represent that. If I want to represent the 0 of the system is in 2, I will represent it. Right? Where pole is the denominator of the system, transfer function of the system, pole is the numerator of the transfer function of the system. So far, is it clear? Give a thumbs up. Okay, rest of the people? Good. So, can I call this as pole and this is 0? Is it clear? Correct? So then the next thing is characteristic equation. If you equate the pole to 0, that we call it as characteristic equation. So this type of system, when you equate this to 0 and factorize it, you will get the poles. pole will be equivalent to characteristic equation. This is the denominator of the transfer function equal to 0. Right, these are all some interrelation between. For example, if you find if I take the denominator, this will be s into s square plus 2h plus 5. This will become s cube plus 2h square plus 5 equal to, I will just, I'm equating to 0, so one s will be equal to 0. The other pole will be s square plus 2h plus 5 equal to 0. So making this, the poles will be into 0, minus 1 plus or minus 0. Another important points about the poles and zeros are, if it is a real value, theta plus j omega, if it is a real value, it will become only zeta. It can be minus or it can be plus. If it is a zeta plus j omega, if it is a complex number, then it will always occur in a pair, not like only minus 1 plus 2j. Never this will exist. If this exists, there is always minus 1 minus 2j. Complex values occurs as a pair, pole pair or zero pair, not like a single value. Otherwise it can be minus 1 or minus 2 or 3, 4, that is independent. The next thing is, whatever value that is there in the left half of the, this is explained, right? This is j omega and this is sigma. So whatever value that comes in the left half of this origin, that we call as left half of the plane, whatever value that is in the right part, it is right half of the plane. So this will be negative, this will be positive. So I will write in differently. This will be negative. This we call as stable. This we call as unstable. So, if any poles, let's say there is a pole in the right half of the S plane, we call this as unstable pole. If there is a 0, then we call it as unstable 0. If there is a pole here, this is stable pole. This is stable 0. What if it is here? How do we call it? If it is straight in the imaginary axis or imaginary, we call this as marginally stable. This marginal stability means whenever you increase the value or magnitude, or whenever you are increasing the number of pole pairs or zero pairs, this might go to this way or this way based on the system nature. It might slip into unstable region or it might come into the stable region. So it is giving an oscillatory behavior. It can become stable or unstable anytime. So we call that as a marginally stable. Right? So for any transfer function, see here it was mentioned in 2, right? So that is a pole. One pole is in minus 1 plus j2. Another pole is in the minus 1 minus j2. Is there any other pole? Here is one pole. So another pole is in 0. There are two zeros. One 0 is in minus 4, another 0 is in minus 2. So this system has 3 poles, 2 zeros. Right? So whenever we are writing the poles in the denominator and we are telling the order of the system using the denominator, we can say, based on this pole, we can say how many number of energy elements are there in the system. Can you interrelate all those things now? Stability, energy elements, number of energy elements, order of the systems and poles. So number of energy elements will be equal to the order, that will be equal to the pole, since all those things are in the denominator. And if the pole is in the left half of the S plane, not it's S plane. Yeah, Nama. Yeah. Yeah, right. You can ask in middle also. No problem. Okay, right. We'll discuss at last. Yeah. So this will be sigma plus j omega, right? So here, based on this, what I was telling, whether this poles and zeros are being the left of phase plane, it will be stable, right of it is unstable, and this we call it as marginally stable. Those are all there in the middle of the imaginary peak, right? Okay. So this is what I was explaining now. You can, when you recall this, you will be able to understand. So mathematically, how this, why we are calling left half as stable and right half as unstable region, that explanation it is given here. So when you consider a system, see, this is a system that where these are all the coefficient, numerator coefficient and denominator coefficient. And this is a transfer function of any system. Considering this as a transfer function of any system where there are n number of poles, right? So this will be written as, if you consider the partial fraction and if you try to find it back, the time domain representation of the system for a single pole, this will be a k into e power at, because s minus a, right? E power at into u of t. Then whenever, since this is a e power at signal, usually this will be like this. E power at in the sense there is no minus. Normally this will be an exponential system. But if the a is minus, then this will become okay. Am I audible now? My earphone got disconnected. Is it too noisy?
Yes, ma'am. Yes, no, ma'am. It's fine.
Okay. Right. Whenever this a becomes minus, this will become a it will not be a, it will be a converging signal, right? So based on the nature of the a, this signal response will get justified. So when the a becomes greater than 0, this will become exponential, exponential become diverges, then this will become unstable. Then when the a will be positive, when it is in the right half of the s plane. When the a is less than 0, it will be the opposite to that. It converges, then it is stable, then whenever it will be stable, it will be in the left half of the s plane. That's why we are telling whenever the poles or zeros are in left half, this will be stable, because the a value will be lesser than 0. Here the a will be greater than 0, right half of the s plane, and this will be unstable, right? These are all the nuances of this poles and zeros. When it's the same thing when it comes to complex poles also. For complex poles also, it should be that sigma value should be negative to make it stable, right? This is the convergence, or this becomes divergence whenever a is greater than 0. Repeated poles in the sense, if we have the same pole repeatedly being here, it will increase the magnitude and it will disturb the frequency over this value. So this makes the system to push towards the right half of the s plane and increases the possibility of making the system to unstable, from marginally stable to unstable. Right, repeated poles means the same poles at different locations at the same frequencies. Sorry, same poles at the same location. Right, please read this properly and understand what it is. Stability relationship with poles, how Bibo stable is related. What are all the things we have discussed so far? This is the summary of this. Right, if any root of the characteristic equation has positive real part, roots of characteristic equation equal to poles. Same thing they will give in different sentences, so that you will try to connect all those points and come to a conclusion. So this will become poles. When the poles has a positive real parts mean A greater than 0, then the signal will be unbounded. As we expected, this will be exponential. Then the system is unstable system. The same thing, but in a different sentence. That's it. So read all these things and you will be able to understand them. So this is one example for marginally stable system, when how the system will be when the poles are at the imaginary axis. So this is the gist. Whenever it is in the left half, poles are zeros, whatever it is. Stable, unstable, whenever it is in this vicinity, it will become marginally stable. Right? So far we have discussed the important concept, what is transfer function, why we are using transfer function, stability of transfer function, what are all poles, zeros, what are all the components of those transfer function. With that pole zeros and components of the transfer function, how we are defining the stability. So these are all things we have seen so far. We can solve some practice assignment problems in the Wednesday class. Meanwhile, I will look upon that graded assignment question number 11 question. Okay, I think that is a mistake from our side. I will speak with the team and let you know about the marks further. If you have any questions, please ask me. Otherwise, you can take attendance and.
Ma'am?
Yeah.
Ma'am, which book should we follow for control engineering?
Nagarath and Gopal book is there. What is the reference book? It was mentioned in the website. I missed to see that. Course introduction page, it should have been mentioned, no? Prescribed books are there. Modern Control Engineering by Ogata. That is a good book. It has some examples also. And Feedback Control of Dynamic System by Franklin. That is a little advanced book than Ogata. You can start with Ogata and go to Dynamic Systems. That's second reference. Right? When you go to next lectures, like after 5-6 lectures, we will not focus more on transfer function. We will go more towards the state space. Then you can make use of the third and the fourth references. Control system design and introduction to state space methods and all. So for now, the first two books are enough. So first start with Ogata. That is a basic book.
Okay.
So, Namai, you have any doubt?
Yeah, ma'am, two doubts. So first I have like a question. Last question 10 and 11 for week 1 rated. Sorry,
Week
11
two.
and 12.
Week 2.
No, ma'am, week 1.
You didn't attend? I didn't get it. What did you say?
Ma'am, week 1, 11 and 12 question rated.
Graded assignment.
Yes, ma'am.
Okay.
And ma'am, the other question was, I just wanted to know how would be the flow for this subject, because, like, very honestly, ma'am, I'm not holding these students. I've been put into all of the classes, also considering like I'm doing an internship at IIT Bombay right now. So, like, it's not like even logistically possible. So, like, is it alright if we ask at the end of the sessions doubts from previous weeks?
Yeah, that is not a problem as long as you are with this week, or you don't bulk up every week and come with like after 7-8 weeks, if you come with first or 2 weeks, it will be difficult. Like
No, that will not happen. It's probably just for the initial few weeks.
Right, no problem. That we can manage.
So, yeah, ma'am, question 1, 11 and 12. Graded.
Question 1.
Yes, ma'am. Week 1, graded assignment 1, question 11, 12.
Question 11, 12. You want to know how to solve this?
Yes, ma'am, if you could just help me with the steps. Like, even if you like do it verbally, I'll understand.
Right, no problem. We will do that. But first of all, I'll take attendance, and if anyone wants to stay to solve this week 1 assignment, you can stay. Otherwise, they can leave. I will guide you, okay?
Sure.
Okay. Please turn on your mic and give attendance. Yeah, Vinayak, okay. Srivastava,
Present, ma'am.
Jamila,
Yes, ma'am.
Sayan,
Present, ma'am.
Namai.
Present, ma'am.
Okay, right. Jamilit, you have asked one question, right? Repeated poles. So when you have a repeated poles at the same location, it will try to induce the oscillative behavior further. So when you increase the frequency of the oscillation further and further based on the number of repeated poles at the same location, it will try to push that system from the marginally stable behavior to unstable behavior towards right half of the S plane. So this is not good for any system, right? It won't, the probability of pushing that system from marginally to unstable will be high, not towards the stable region. It won't push it towards stable, it will try to push it towards the unstable. So when you increase the oscillation further and further, the system tends to fail, tends to go into the unstable region. That is why you should not have too many repeated poles at the same location. For example, 4 minus 1 plus 2j minus 1 minus 2j pole pairs. This will affect the system. This will not make the system at the marginal stability. It can push it to unstable. I'm not saying it must, it may, right? Clear? Right. Rest of the people can leave. And if you want to stay back and see week 1 assignment, that 11 and 12 problem, you can be here. Otherwise, you can. Thank you for joining. Right, I will share my screen now. Okay. The 11th question is, consider the equation of pendulum of lecture 5 and which of the following represents an undamped system. Okay, fine. For this, you should understand what is undamped system, right? First of all, we'll look what is the equation of pendulum in lecture 5. Wait a minute. Right. So this is the equation of the simple pendulum. Okay. We are going to consider this equation, and the question is, which of the following represents an underdamped system? Right. That is the question. Underdamped. Okay, I was telling in the class about the second order systems, where the second order systems can be represented using this representation, where this will be s square plus 2 zeta omega n s plus omega n square. Okay, this is a representation, general representation of any second order system, where this omega n called as natural frequency, and this zeta represents this damping ratio. So the damping can be like whenever you have a door for your AC room. So if you sometimes in some computer labs, if you leave the door, it will just come and slam the frame, right? So sometimes it may come slower, very slow, and it will not close properly. So this damping constants is a reason behind that. So how much you are increasing it? It could be from 0 to 1. How much you are increasing this damping ratio or constant, that's how the behavior of the spring will work. Like how slow or how speed you want the door to come back to the original position, and how much good it is going to close the door. So based on this zeta value that varies from 0 to 1, we are classifying the system into undamped, underdamped, critically damped,
Right.
and overdamped. Right, but when undamped means zeta will be 0, underdamped will be zeta will be 0 to 1 within this region. Critically means zeta will be exactly equal to 1. When zeta greater than 1, this we call it as overdamped system. So based on our question, we are going to focus on this region. Your zeta should be 0, lesser than or equal to zeta, less than or equal to 1. Okay, right? This region we are going to focus. The question is, we have this equation here. They have asked, consider this equation of pendulum and which among the represents the underdamped system. Okay. Now, when you look for option B, when option is equal to B, where this TF equal to B theta, right? This B they have represented. So when in this equation, when the B becomes 0, you will left with this equation, right? These two equations. That will be lossless system, right? Will this equation becomes a underdamped system? That's what they are asking. Based on the B value, will the equation becomes underdamped? So when you take a Laplace transform of this since it is a theta double dot, this will become s square something, right? S square theta of s.
S squared theta plus there's then also this term of S0.
Yeah.
Assuming the 0 part is 0, right? That's what we're assuming.
Yes, but with friction, if you consider, this will become S into B by ml square into theta of s plus G by L into sine of theta of s equal to 0. I'm going to tell everything in terms of Laplace equation. So when I put B equal to 0, this term will go to 0. This whole term will go to 0. There will not be any S term. So when you compare this with this, then the zeta will be equal to 0. Is it underdamped system? Is it underdamped? I'm asking.
Ma'am, after we take the Laplace, right?
Yeah. Laplace
So
of
we
this
get,
equation.
What did you write down?
Here. Here,
This.
This will become theta double dot become s square theta of s minus of some initial condition. Just consider initial conditions as 0.
Right.
Right? Then this second term become s into this constant that considered b by ml square into theta of s.
Right.
Plus g by l sine of theta of s, it will be kind of constant, it will be. So when you consider option A in the question 11, b equal to 0 for any positive values of m and l, right? Rest of the things are some positive values, but when you consider b as 0, this whole term will go to 0, right? 0 into anything will go to 0. You will be left with h square term and some constant term. Is it clear this thing whenever whatever I am saying?
Yes.
So when you compare this with this standard equation, you will get zeta equal to 0, right? This standard
Right.
equation. So zeta equal to 0 will not be underdamped system. Your question should be you should find zeta so that the system will be underdamped. When you put b equal to 0, it becomes undamped system. So you should omit option A.
Ma'am, could you write the equation also? I'll just write it, like, note it down.
Okay. Okay, this with friction, simple pendulum will be theta double dot plus b by ml square theta dot plus g by l sin theta equal to 0. Then when taking Laplace transform, this becomes s square theta of s plus b by ml square theta of s, s into plus g by l into sin theta of s equal to 0. So this will become, so when I put b equal to 0 here as in question number 11 option A, this becomes s square theta of s plus g by l sin theta of s equal to 0. When I compare this with the standard equation, that is s square plus 2 zeta omega n s plus omega n square equal to 0. So there is no s term here, right? There are s square term, there are constant term. So this gives zeta equal to 0. This becomes undamped system, not underdamped. But the question they have asked is how to make this as a underdamped system. So the option A of putting b equal to 0 is a worse idea.
Oh, right. Understood.
Right. If you put b equal to -1, you have to find the same calculation. When you put b equal to -1, you will get, but zeta will be negative. Then this will also be not recommended. But whenever you are putting option C and D, b equal to 0.1 or b equal to 1 for any positive values of m comma l, you should consider this also, right? Greater than 0, m comma l. Then this will be in the bound. This will make the zeta to be in the bound 0 less than or equal to zeta less than or equal to 1. So these two options will make the system underdamped. So the right option should be C and D. Right?
Okay, right.
Similarly, you put the combination for B, M, L in 12. Same thing. Put all the M, L. They have given, instead of giving only the positive value, they have given ML value itself. Just replace the equation with ML and B and see for what values the zeta is in between 0 to 1. Then that option should give you a underdamped system. Clear? Is it clear, Mama? I think you're on mute.
Yes, ma'am.
Right, okay. Fine. Do you have any other doubt?
No, ma'am, I think that's all.
Right, okay. We'll see you in the next class, Wednesday class, okay?
Sure, ma'am, sure.
Thank you, Namai. Thank you, Jamila. Bye.
Thank you.
Yeah, Jamila, do you have something to say? Are you typing? Right. Week 1, graded assignment, 12th question, option C is right. Option A and D are right. I think you have made some calculation mistake. Correct option will be A and D. Okay? See you. Bye.